Welcome to Lecture 29, in which we will put together several of the ideas we've been talking about in recent lectures. And I want to, this whole lecture will concern the following problem. We want to find a circuit for which the matrix relative to the standard basis is And by the way, this problem is one that I found in the Nielsen and Chuang book that we will be using next semester. So here is the matrix for the circuit. And we want to find the circuit. Now we're using the standard basis, and so that means that our basis is the following. And this is in the correct order. Which means that we associate with the 0, 0, 0 state the vector 1, 0, 0, 0, 0, 0, 0, 0, 1 and 7 zeros. And then with this state 0, 0, 1, we associate 0, 1, and then 6 zeros, and so on. So this means that if we consider the first input bit to be X, and the second input bit, if we call that Y, and the third input bit we call Z, and if we let the first output bit equal X O and the second output bit be Y O and the third output bit is equal to ZO, then we can form the following truth table. We have X, Y, Z, XO, YO, ZO. Now let's figure out how to fill in the information for XO, YO, and ZO. Okay, so when X and Y and Z are 0, this means we are in the 0, 0, 0 state, because remember, X is the first input, I should say here, qubit, actually. So this is the qubit, and the same all the way down. And likewise down here, I'm thinking of qubits. So X is the first qubit, Y is the second qubit, Z is the third qubit, and those are all qubits of the input. And then XO, YO, and ZO are qubits of the output. Once again, first, second, and third. And so when the input qubit, the input state is 0, 0, 0, okay, we're in the first column. And we see that the image of that is this vector, 1 and then 7 zeros, which corresponds to the 0, 0, 0 state. So when we input the 0, 0, 0 state, we get out the 0, 0, 0 state. So far, so good. Now the second column is the image of 0, 0, 1. And notice that this second column corresponds to the vector that we associate with the 0, 1, 0 state. So 0, 1, 0 is our output here in the second row. And similarly, here for the third column, this is the image of 0, 1, 0, and this vector corresponds to 0, 1, 1. And so we just continue in this same fashion. We'll have 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And then finally, for the last column, we have 0, 1, 0, and the rest zeros. And that is the vector corresponding to this 0, 0, 1 state. So here we have 0, 0, 1. And that takes care of the truth table for X0, Y0, and Z0, or actually XO, YO, and ZO, in terms of the input variables X, Y, and Z. So now that we have this information, we can find a Minterm expansion for each of these functions. And let me show you what I mean there. Okay? Since XO is equal to 1, when X is 0 and Y is 1 and Z is 1, that means that XO is equal to X prime Y Z. Notice that this expression right here, this is a Minterm because it involves all of the input variables. And likewise, it is equal to 0 for all possible combinations of these variables except for the combination 0 for X, 1 for Y, and 1 for Z. So this term here will give us this 1 in the XO column, and only that 1. That's the only occasion when this term is equal to 1 is when X is 0, Y is 1, and Z is 1. So we have that 1, but now how do we get this 1 as well? Well, we'll put in an OR here, a plus, and to get this second 1, we need X, Y prime, Z prime. X, Y prime, Z prime. And similar to what we had before, this is a Minterm, and it's equal to 1 only for the combination 1, 0, 0. For all other combinations, this would be equal to 0. So now when we consider these two together, they will be equal to 0 everywhere except in these two cases. So now we have two of the 1s accounted for in this column. And we have two more to account for, and I encourage you to take a break for a moment, try to do this yourselves, and then we'll do it together. Okay, to take care of this one, we need to include x, y prime, z. That will take care of this one, x, y prime, z. And then finally, to take care of this one, we need x, y, z prime. And I'll go ahead and write, because what we're going to do now is use the Quin-McCluskey method to find hopefully a more efficient expression for x naught. And we know that in the Quin-McCluskey method, that one of the first things we want to do is to find a binary representation for each term. So let me go ahead and write those down. We'll have 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. Okay, that's x0. Now let's look at y0. Again, I would encourage you to try to do y0 and z0 on your own and then compare with what we will get. Okay, the first one in y0 corresponds to x prime, y prime, z here. The second one corresponds to x prime, y, z prime. That's right here, the third row, x prime, y, and z prime to get that one. And then down here for this one, we have x, y prime, z, x, y prime, z. That's down here in the sixth row, x, y prime, z, to get this one right here. And then finally, x, y, z prime to get this one, or x, y, z prime. And let's write down the binary numbers for each of those. We'll have 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0. And I believe everything looks good. Okay, and now let's go ahead and finish this up. Before we go ahead and do the Quin-McCluskey method for each one, let's just go ahead and find out the information for ZO. The first one corresponds to x prime, y, z prime. Right here in the third row, x prime, y. Here's x prime, y, z prime to take care of this one. For this one right here, we have x, y prime, z prime, x, y prime, z prime. That takes care of this one. For this one down here, we will have x, y, z prime. And then for this final one in the ZO column, we have x, y, z. And so we have 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1. And I believe we're all in good shape now. So we now have XO, YO, and ZO expressed in terms of the input variables X, Y, and Z. And now we want to make these, notice that at this point each one of them is we have a Minterm expansion for each one of these, and each one is expressed as the sum of 4 Minterms. But now we hope to get more efficient expressions, and so we're going to use the Quin-McCluskey method for each one of these. And I'm hoping that this won't take too long, but we'll see. So XO will be first. and let's say no ones. Okay, there isn't anything in that category for XO. Each one of these terms has at least one 1 in it. So now let's go to the next one. 1, 1. And the 1, 0, 0 term is the only one that we'll have there. So we have 1, 0, 0, and that is X, Y prime, Z prime. And then we have 2 1s, and that actually is the rest of the terms. So we have 0, 1, 1, 1, 0, 1, and 1, 1, 0. Those are the rest of the terms there for XO. Now let's go ahead and write down for each one of these the decimal equivalent. This is the number 4. 0, 1, 1 is the number 3. 1, 0, 1 is 5. And 1, 1, 0 is 6. And let's write down the variables for each one as well. 0, 1, 1, you can see is X prime Y Z. 1, 0, 1, right here is X, Y prime Z. And 1, 1, 0 is, as we can see up here, X, Y, Z prime. So it looks like this won't be too bad, but let's check and make sure. Since we don't have anything in the no ones category, we don't even need to consider that anymore. So we'll go to 1, 1. We'll start there for our second column. Now, remember, we don't need to consider 4 combining with 3 because 4 is larger than 3. And notice, even though the difference between these two numbers is 1, which is a power of 2, since the upper number is larger than the lower number, these cannot combine. And sure enough, if you try to combine, you'll see that these two terms indeed cannot be combined. So we don't have to worry about that one. But the next one is 4 and 5, and in that case, the upper number is smaller than the lower number, and the difference between them is 1, which is a power of 2. So these should be able to be combined. And we notice that these differ only in the Z position. So that will drop out, and we'll be left with XY prime. So we have XY prime, and that is the result of combining 4 and 5. And we need to put a check by 4 and a check by 5. Likewise, 4 and 6. 4 is less than 6, so that's good. And the difference between 4 and 6 is 2, which is a power of 2. So these two should be able to be combined. They differ only in the Y position, so Y will drop out, and we'll be left with XZ prime. XZ prime, and that's the result of combining 4 and 6. And we already have a check by 4, but now we'll put a check by 6. And that's all of our combinations that we can have. That's it. And so now we look at the unchecked terms. And so we have unchecked terms. I'll put it here. Unchecked terms. And those will be X, Y prime. Well, let me write them in order. So starting in the first column, we have X, Y prime, Z, which is the term 3. And then we have X, Y prime. I'm sorry, I looked at the wrong one there. That's not X, Y prime, Z. That's X prime, Y, Z. So X prime, Y, Z. Okay. And then we have XY prime, which is the combination of 4 and 5. and xz prime, which is a combination of 4 and 6. So there is our vertical listing of all the unchecked terms, and now on the top we want to list horizontally all the terms that are in the function. Now this first one, 0, 1, 0, that is 2. Where did that go? Oh, well, we made a mistake here because that was not included in the... sorry, I'm looking up at Z0. Here we go. We're doing the XO right now. So 0, 1, 1 is 3. The next term in XO is 1, 0, 0, so that's 4. The next term is 1, 0, 1, that's 5. And the last term in XO is 1, 1, 0, which is 6. So we, from the first row, we have an X in the column marked 3. In the second row, we have X's in the columns 4 and 5. And in the last row, we have X's in 4 and 6. And you can see that each one of these terms must be included. How do you conclude that? Well, the X in column 3 tells you that the first term must be included. Because this is the only X in that column, so we must include the corresponding term. And the X in column 5 tells you, again, it is the only X in that column, so we must include the second row term. And finally, this X in column 6 also stands alone, so we must include this third term. So our minimal sum expression for XO will be XO equals X prime YZ or X Y prime or X Z prime. And that finishes our work for XO. Now, I very strongly encourage you to stop the video at this point and to try to find the minimal sum expressions for YO and ZO, and then after you've done that, come back and watch as we do it here and see if you get the same results. Okay, now we'll do YO. And for YO, the terms that we have are, you can see up here, 001, 010, 101, and 110. I think I'll go ahead and transfer that down here. So 001, 010, 101, and 110. Which is, in decimal form, that will be 1, 2, 5, and 6. So now if we group these, there's no terms with no ones, so I won't even put that grouping this time, or that category. 1, 1. Well, we have 0, 0, 1, which is the term X prime, Y prime, Z. And we also have 0, 1, 0, which is X prime, Y, Z prime. And those are the only two terms with 1, 1. And then we also have two terms with 2 1s. 2 1s. We will have 1, 0, 1, which is x, y prime, z. And we also have 110, which is x, y, z prime. So now we start checking these 4 combinations. So we come to the second column now, 1, 1. And what about 1 with 5? We expect that to work because 1 is smaller than 5, and the difference between 1 and 5 is 4, which is a power of 2. So we expect 1 and 5 terms to combine. Notice that they differ only in the x position, so that will drop out, and we should be left with y prime z. Y prime z. And if you compare these two terms here, that is indeed what we will get, and that's the result of combining 1 and 5. We don't expect 1 and 6 to be able to be combined because they differ by 5, which is not a power of 2. And indeed, if you check them, you see that they differ, in fact, in every position. So they cannot be combined. What about 2 and 5? No, they differ by 3, which is not a power of 2. But what about 2 and 6? Yes, those should be able to be combined. Oh, by the way, before I go any further, let me put the check mark by the term 1 and a check mark by the term 5 here. Okay, now 2 and 6, if you look, these two differ only in the x position, and so that x will drop out and we'll be left with yz prime. And sure enough, if you look at the terms, that's what we get. And so we get a check mark by 2 and a check mark by 6. And that's the end of the first column. And of course, there's nothing we can do now with this second column because it has only one category in it. So we're done. We have our, so now when we look the unchecked terms, or just those two terms in the second column, we have y prime z and y z prime. Y prime z is 1, 5. Y z prime is 2, 6. And now we list horizontally the terms in the YO function, which are 1, 2, 5, and 6. And you can see that in these cases, the Quin-McCluskey method is not so bad. It's going pretty quickly. And we get 1, 5, 2, 6. And every one of those x's is alone in its column, and therefore both of these terms here are necessary. So we get minimal sum expression for YO is equal to y prime z or y z prime. And so now we're down to the last one, ZO. And for ZO, we have, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, and 1, 1, 1. 1, 1, 0, 1, 1, 1. Just to check, yes. Okay. So now, again, there are no terms with no ones, so we start with 1, 1, 1, 1. Oh, and by the way, let's go ahead and put the decimals down here. This is 2, 4, 6, 7. Okay, so 1, 1, we have the 0, 1, 0 term, which is x prime, y, z prime. And we also have 4, 1, 0, 0, which is x, y prime, z prime, and there are no other terms with only one 1. What about 2 1s? Well, there's one of those terms. It is 6, 1 1 0, which is x, y, z prime. And then 3 1s. There's one of these terms this time, and it is x, y, z. So now let's see what happens here, okay? 1 1 will be our first category in the second column. Do we expect 2 and 6 to combine? Yes, because 2 is smaller than 6, and the difference between 2 and 6 is 4, which is a power of 2. And so 2 and 6, if we look, indeed they do combine. The x term is the one that differs, so it will drop out, and we'll be left with yz prime. Yz prime, and that's the result of combining 2 and 6. So 2 gets a check, and 6 gets a check. What about 4 and 6? Yes, those should combine, because the upper number is smaller than the lower number, and the difference between 4 and 6 is 2, which is a power of 2. And when we look at 2 and 6, we see that they differ in the y position, so that drops out, and we're left with x z prime. X z prime. And 6 already has a check by it, but now 4 will get a check. So that's all for the elements in group 1. We don't check for group 1 terms combining with group 3 terms, only with group 2 terms. So 2 and 4, both of those terms combine with 6, and now we look for 6 combining with 7. So our next grouping here will be 2 1s. And we do indeed expect 6 to combine with 7, because 6 is smaller than 7, and the difference between them is 1, which is a power of 2. So we'll go ahead and put down here 6 and 7. We expect them to combine. Notice they differ only in the z position, so that drops out, and we're left with xy. And 6 already has a check by it. Now 7 gets a check. Now this is the only time here in the 3 cases we've looked at, this is the only time where there's anything to do in the second column, because notice for XO there was only one category in the second column, so obviously those terms can't combine with anything else. And likewise only one category in the second column for Y0. But for ZO we have 2 categories here in the second column, so we at least need to check it, but notice that neither one of these terms will combine with this term, because the 2 variables here are y and z, the 2 variables here are x and z, and neither one of those matches this, which is x and y. So we are done. And now the unchecked terms will be yz prime, which is 2 and 6, xz prime, 4 and 6, and xy, which is 6 and 7. Those are terms, and are vertically arranged terms, and our horizontally arranged terms must be 2, 4, 6, and 7. So the check marks fall in this fashion. And you can see, because this x in column 2 is by itself, the yz prime term is necessary. Because the x in the column 4 is by itself, xz prime is necessary. And because the x in column 7 is by itself, the xy term is necessary. So all 3 of these terms are necessary, and the minimal sum expression for for ZO is ZO equals YZ prime or XZ prime or XY. And now we have found minimal sum expressions for each of our three output variables, XO, YO, and ZO. Let's put together all of these expressions here. So for XO, we had X prime YZ or XY prime or XZ prime. For YO, we obtained Y prime Z or YZ prime. And for ZO, we obtained YZ prime or XZ prime or XY. Now, at this point, I'd like to make one observation. We see that YO here is equal to Y prime Z or YZ prime, which of course is the same thing as Y exclusive ORed with Z. Now, we don't want to mess up the lines carrying Y and Z very early in the process, because we will need those to construct XO and ZO. But if we construct XO and ZO first, then and then construct YO in the last step, what we could do here, since we have that YO is equal to Y exclusive or Z, we could have a controlled NOT gate to get YO from the Y and Z lines. We could have the Y line controlling the Z line, and then Y0 would appear on the Z line, or we could have the Z line controlling the Y line, in which case Y0 would appear on the Y line. But if we did either one of these things, then it would mess up Y and Z for us. They would no longer be available for any subsequent calculations that we wanted to make. And so therefore I will not use this approach. What I will do for all three of these is to now use the kind of approach that we had in our last lecture, where we try to write each one of these entirely in terms of NAND gates, AND gates, and NOT gates, because all of these can be easily implemented with Toffoli gates, and then we will be able to write X0, Y0, and Z0. Hopefully, we will be able to generate those hopefully in an efficient way, and also in a way that does not destroy the availability of X, Y, and Z. And you'll see what I mean by that in just a moment. So I encourage you now to stop the video and to try to write each one of these entirely in terms of NAND gates, AND gates, and inverters. And the answer is not unique. Different people might get different answers, but let's see if you can do that, and then let's come back and you can check on what I'm doing, and we'll finish this problem. Okay, so for each one of these, my approach would be as we did in the last lecture, which would be to invert each one of these twice. So we have x prime y z, or x y prime, or x z prime, and that's primed and then primed again. And again, what we're going to do is keep that outer prime right where it is, but the inner prime we will handle using De Morgan's theorem. So the complement of a sum is the product of the individual complements. So we have x prime y z complement ANDed with x y prime complement ANDed with x z prime complement. And we're not ready yet, because notice that this cannot be implemented here because this is would be a 3-input NAND gate. So now this could be implemented with a 2-input NAND, and this could be implemented with a 2-input NAND, and then we could AND those two things together. So we're in good shape here, but we need to look at this term in a little more detail and see what we could do there. Well, notice that if we had y ANDed with z, if we had that calculated, then this could be calculated with a 2-input NAND gate. So what I'm saying here is that we can think of this in the following way. We'll have x prime, and then we have y ANDed with z, and then the result of that will be ANDed with x prime, or excuse me, will be NANDed with x prime. And then x ANDed with y prime, or NANDed with y prime, and we could perhaps AND those two things together, and then we would NAND that with x z prime, the NAND of that. And you'll see exactly what I mean in case that's at all hazy. That will become clear when we actually draw the circuit. Okay, so that's what we have for XO. And now for YO, Y prime Z, or YZ prime. Prime, prime, and so this is y prime z prime, y z prime, prime, and then that is primed, and we're all in good shape there now already, because this is a 2-input NAND, and here's a 2-input NAND, and then once we get those two results, then another 2-input NAND of those two results will give us YO. And then finally for ZO, we have YZ prime, or XZ prime, or XY prime, prime. And so this gives us YZ prime, prime, XZ prime, prime, x, y prime, and then that's primed, and so finally we can write this as y z prime x z prime. We can generate those two results with two input NAND gates, and then we can AND those two things together, and the result of that can be NANDed with xy prime, which can be obtained with a two input NAND gate, and we'll have a CO. And by the way, I didn't put the last set of parentheses down here with XO. We could do this in a couple of fashions. Maybe let's do this. Okay. So now let's we have all of our expressions, and so now let's try to implement this. And now, what we would like to do is the following. We'll have one line for x, one line for y, and one line for z. And then we also have 3 lines, which we will initially, we can have either 0 or 1 on these lines. For right now, I'll just say 0, 0, 0, but we might change our mind to 1s. But we'll have 3 more lines, which will, over here at the extreme right, those 3 lines will become XO, YO, and ZO. Now, ideally, we won't need any more lines than this, but I think that in this case we certainly will need some more lines. And furthermore, I don't think that this is going to be enough room for us horizontally. So rather than trying to put this all together in one circuit, I'll just make 3 separate circuits. Well, let's just see how it goes. Let's see what we can do. So let's draw our horizontal lines here. This is for X and Y, Z, and I'll move these over. XO, YO, ZO. Actually, well, let's just leave it like that. And let's try to construct XO first and see how this will go. So if we take the approach first of trying to construct this term, well, I tell you, I'm determined not to make this lecture too long, and I think that to entirely construct the term for XO and ZO and YO would take far too long. So let's just try to construct the term for YO, and then we can save the rest of this for the next lecture. I think if we'll merely construct the term for YO, that will be enough to allow you to do a reasonable problem for this lecture. Okay, let me make a couple of changes here. After looking at this in more detail, I think it'll be more convenient if we put our work lines or scratch lines, whatever you want to call them, immediately below our input lines, and then put our output lines at the very bottom. Now, I'm not sure how many of these scratch lines we'll need. Actually, in the case of calculating YO, we can get by with just 3 of these, but in order to calculate XO and ZO, we might need more. so let's just, as I say, for right now we're calculating YO, so as we will see, it will suffice to have only 3 work lines, and then I'll put one more line here. This will be YO. And it looks like somehow my pen has gotten messed up, so let me investigate this and then I'll resume. Okay, so now I have this solved, I believe. I'm not sure why that got changed, but it did. So as I said, I'm going to have one more line here for YO. Okay, so I'm not sure when this started recording again, but this is fine. And so, as I said, I have one more line for YO. And furthermore, as we will see, it's going to be convenient to have 1s on each of these lines, on our scratch lines. It will be convenient to have 1s rather than 0s, and we'll see why in just a moment. And a 1 also on that last line, which will become YO. Okay. So now I believe everything is in order, and let's see how this will go. So again, right now we're trying to find a circuit for YO. And you can see here, right in the middle of the screen, that YO is equal to Y prime Z, and then that needs to be NANDed together. YZ prime need to be NANDed together, and those two results need to be NANDed together. And so I will show now a way to do this. Okay, well, first of all, let's worry about this first term. How can we get Y prime? Well, if we have a controlled NOT gate, and the controlled NOT gate can be very easily constructed from the Toffoli gate by just setting one of the inputs to 1. So we could have a Toffoli gate here if you wished, and have the other input have 1 here on another line, and that 1 and Y could be the control lines, and this can be the controlled line. So if you're not satisfied with the controlled NOT gate, then that's the way you could get rid of this and use Toffoli gate. But for this purpose, we'll just go ahead and use controlled NOT. So and the reason you can see now why the 1 is convenient, because we want this to be Y prime, and of course if this were 0, then we would get a Y here. But if this is 1 and it's being controlled by Y, then just keep in mind this will be 0 when Y is 1, and it will be 1 when Y is 0, and therefore this is going to be Y prime. And I'll just make a little note here that we will have Y prime here on this line after that controlled NOT gate. Now we want to have Y prime ANDed, well, actually Y prime is going to be NANDed with Z according to this. So how can we accomplish that? Well, if we have Z and Y prime, and then put an X here, then this would give us on this line Y prime Z NANDed together. again, if this were 0, then we would get y prime and z ANDed together. But this says we want them NANDed together, and so it's convenient to have a 1 here. So we have created the y prime z NANDed together in just this way. And having seen that, I'm sure you can see how we can get z prime y as well. Let's first do the z prime. So we can construct z prime like this. That would give us z prime here. And then we want to NAND z prime with y. So let's think for a moment about that one. Well, we want to NAND z prime with y. And you might be thinking that the obvious way to do this would be to go ahead and use the z prime line that we've just created, use that as one control, use y as another control, and then use this last one line as the controlled line, and then that would give us z prime and y NANDed together. And that is indeed one route that we could take, but then that would put that z prime y NANDed together on our last line, and the last line is the one that right now we're trying to reserve for y0. So what can we do? Now keep in mind, we don't know anymore. We don't have a 1 here on the line above, and furthermore we don't have a y on this line. Excuse me, we don't have a 1 on this line either. So one possibility would be to just create another line with a 1, but we would prefer not to use too many of those scratch lines. So there is, fortunately, another option. Okay, notice that since we have already created this y prime z NANDed together, we've put that on this line. We now no longer need to have this y prime on this line. So what we could do in this case is we could I'm just trying. Well, one thing we could do is we could put another gate like this, another controlled NOT gate, and that would give us back here a it would undo the action of the first controlled NOT gate and give us back a 1 here. So why don't we go ahead and take that approach? So we'll again, if we put this controlled NOT gate here, notice that there's nothing else. This y prime that we created on this line, it is not getting changed any by this gate or this gate. So if we put another controlled NOT gate here, that will give us back a 1 on that line. And now we have the NAND of y prime z on this line, and we have z prime here. So if we take the z prime line as one of our control lines, and the y line as another control line, and this line on which we've put the 1, use it as the controlled line. Now we know that there's a 1 there, but now that we we place this gate, and we will have y z prime on that line. And now the last thing we want to do is to take the y prime z prime here. Notice that's the first term here. And here's our y z prime, which is the second term, and we want to NAND those two together. So we'll take this and this down here to this line, which has a 1 coming in, and we should get YO is equal to well, I'll just say y prime, it should be equal to the desired value. Now, after we've done that, we would like to recover 1s on all of our scratch lines here. These are our 3 scratch lines, and we'd like to recover 1s on all of those. So we know that if we put the inverse of this gate here, we'll get back the 1 that we had there. So let me put that there. And that will give us back a 1 on this line. And now if we will put this gate again, that will give us a 1 back on that line. So now we have a 1 on the first scratch line and a 1 on the third scratch line. And what about this second scratch line here? Let's think about that for a moment. Well, to be honest, when I begin to look at this, I think this is, it's just taking too much time to do this, and we don't want to have that approach. So let's just say that one way we can easily guarantee the result we wish is the following. Okay, so we will okay, perfect. So here we have created the output that we want, and now the way that we can make sure that all of our scratch lines are equal to their original values is now that we've created our output. Now to the right of the output, we just go in backwards order everything that we've done, and it may be a little redundant. There may be some things in there that we don't need, but if we do that, we'll make sure to reverse everything and return all this to 1. So here again is our result of Y0. So this gate, we'll undo this one, and then we would have this one, this would undo that, and then we could put this gate to undo this, and then this gate would undo this one, and then finally if we do this, so notice that here's the line, here's the final line, the final gate that calculated our output, and everything besides that, everything is symmetric about that, and so that means that we will still over here have X, Y, and Z, but not only that, but all of our scratch lines will be at 1, and so now we could continue on from that point and make XO and ZO as well. But again, those would be even a little more complicated than YO, as you can see, because they are somewhat lengthier terms. But this is the main idea of how to conserve on terms, and your book talks about this in some detail, but this is the general idea, this idea of undoing some of your work to conserve on the number of scratch lines is an issue that they stress in your text. And so this is what they mean by that. This is an example of what can be done. So now let's look at the problem for lecture 29. We'll have one lecture problem and one in-class problem. They will both be similar. I intended for the one in lecture to be a bit easier than this. But since you have more time to work on this one, this is what we'll have. And keep in mind, for this circuit, and likewise for the one here, and for the ones that we, to be honest, I'm not sure. I'll try to include these at the beginning of the next lecture after all, because I imagine that you get the idea of this, and so I'm not sure that it's really worth the effort to make these involved circuits. But following these principles, we make circuits that are efficient, but by no means is there the claim that these are the most efficient circuits that could be made. It's just that by using the technique shown here of undoing the gates once we've calculated our result, and thereby recovering our initial values on these scratch lines, by using that technique, we do help to reduce the overall number of scratch lines needed for a more involved circuit. And so, anyway, getting to this problem for this lecture, what I'm asking you to do is, if these lines are as shown here, and we define this line to be x0 and this one is y0, to find the matrix for this circuit. So I think I'll leave it at that, and that concludes lecture 29. And as I say, the in-class problem will be very similar to this. So that concludes lecture 29, and good luck.